In this tutorial we're going to look at series parallel circuits. We're going to do this by applying the current divider formula and voltage divider formula to the circuit shown. Using these formulas we'll calculate the current through each resistor and the voltage across each resistor. To use these formulas we need to first know the total circuit resistance. The easiest way to calculate the total circuit resistance is to calculate the resistance of small sections of the circuit one at a time and then adding these resistances together. This can be done in any order. So for example, we can begin by calculating the resistance of resistors R3 and R4 in parallel and then calling this resistance RA. You can see that the resistance of these two resistors in parallel would be 1 over R3, which is the resistance of the first branch, plus 1 over R4, which is the resistance of the second branch, and this will give us a resistance of 956 ohms. Next, it can be seen that resistor R6 and R7 are in series, so these resistors can be added together to give us resistor RB, which will work out to be 2.4 kiloohms. The next step I'm going to take is to calculate the total resistance of this branch shown. This resistance I'm going to call RC, and it's equal to R11 plus R14 added to the resistance of R12 and R13 in parallel. This will give us a resistance of 3,956 ohms. So we can then replace the resistors highlighted with resistors RA, RB and RC, giving us the circuit shown here in the bottom right. Now we can simplify this circuit down even more. So to begin with, we're going to work out the resistance of resistors RB, R8 and R9 in parallel, and we're going to call that resistance RD. This works out to be 885 ohms. The next step I'm going to take is to work out the resistance of resistor R10 and RC in parallel, and this works out to be 921 ohms. This leaves us with the circuit shown here on the right, where now we have all resistors in series, and we can simply add these resistor values R1, R2, RA, R5, R9 and RE to get the total resistance of this circuit, which works out to be 8,762 ohms. Now that we've got the total resistance, we can start using the current divider and the voltage divider formulas. To begin with, we'll first use the current divider formula, so we first need to calculate the total circuit current, and it can be calculated by dividing the supply voltage Vs by the total circuit resistance, giving us a total current of 17.1 milliamps. It can be seen that this I total will flow through resistor R1 and R2, which are in series. So straight away we've calculated IR1 and IR2 to be equal to I total. This current is then going to flow into a node and split up into two branches, with some of the current flowing through R3 and some of the current flowing through R4. So we'll calculate these two currents next. So using the current divider formula, we know that the total resistance of this parallel section of the circuit, which we calculated earlier to be RA, is equal to 956 ohms. So we're going to put that over the resistance of the branch that we want to calculate the current through and multiply it by the total current that flows into this node as shown, and this will give us a current of 13.62 milliamps. Next we'll calculate the current that goes through R4. So again, we know the total current going into this parallel section is 17.1 milliamps. So we'll multiply that by the total resistance of this parallel section, which again we worked out earlier to be 956 ohms, over the resistance of the branch that we want to calculate the current through, and we see that the current going through R4 is 3.48 milliamps. So when you add IR3 and IR4 together, as stated by Kirchhoff's current law, it'll add up to the total current that flows into this junction of 17.1 milliamps. So the current going through IR3 and IR4 will join up together again to become I total, which will flow through R5. So we can see that IR5 equals I total, which equals 17.1 milliamps. This current now is going to flow into another parallel section where it will split up into 3 different branches. So some of the current is going to flow through R6 and R7 in branch 1. More of the current will flow through R8 in branch 2, and the remainder of the current will flow through resistor R9 in branch 3. So again, we're going to use the current divider formula, and we know that the total current flowing into this parallel section is 17.1 milliamps. We know that the total resistance of this parallel section, which we worked out earlier as RD, which worked out to be 885 ohms. So to get the current flowing through through R6 and R7, we multiply the total current flowing into this parallel section by the resistance of this parallel section of 885 ohms over the resistance of this branch, which is, we worked out earlier to be RB, which is R6 and R7 added together, and we get a current going through this branch of 6.3 milliamps. Next, we'll calculate the current flowing through resistor R8. So again, we know there's 17.1 milliamps flowing into this parallel section. We multiply that by the resistance of this parallel section of 885 ohms over the resistance of resistor R8, as we want to get the current going through this branch, and we get a current value of 3.22 milliamps. Next, we calculate the current going through R9. So again, we multiply the current flowing into this parallel section, which is 17.1 milliamps, by the total resistance of this parallel section, which is 885 ohms, over the resistance of the third branch, which is 2 kiloohms, and we get a current of 7.57 milliamps. So you see, when we add the current through each of these 3 branches together, they add up to 17.1 milliamps. The current from each of these 3 branches then join up together to form I total again. This current I total then flows into the next parallel section. So to begin with, we're going to calculate the current going through the top branch of this parallel section, which is the current flowing through resistor R10. This is calculated by multiplying the total resistance of this parallel section over the resistance of R10 by the total current that flows into this parallel section, and we get that 13.1 milliamps flows through resistor R10. Next, we're going to calculate the current that flows through the bottom branch of this parallel section, and this will be the current that flows through resistor R11. This is calculated by multiplying the total resistance of this parallel section over the resistance of this bottom branch by the total current, and we get that there's 4 milliamps of current flowing through R11. This current is then going to flow into a junction and split up into 2 paths, with some of the current flowing through R12 and the remainder through R13. To do this, we must first calculate the resistance of this parallel section, as we've not done so previously. So we'll call this RF, and we can now calculate the current going through R12. So it's going to be equal to the total resistance of this parallel section RF over the resistance of R12 multiplied by the current which is flowing into this parallel section, and we get to this 3.2 milliamps of current flowing through R12. Next, we calculate the current flowing through R13. So it's again equal to the total resistance of this parallel section RF over the resistance of resistor R13 and multiplied by the current flowing into this parallel section, and we get to the 0.8 milliamps of current flowing through resistor R13. So we can see the current going through resistor R12 and the current going through resistor R13 add up to the 4 milliamps of current that's flowing into this parallel section. This current then joins up together again and flows through R14, so we know that there's 4 milliamps of current flowing through resistor R14. The current going through this top branch through R10 and through the bottom branch will then join up together again to become the total current, and this current will continuously flow around the circuit. Next, we're going to calculate the voltage across each resistor using the voltage divider formula. So we'll start with resistor R1, and to calculate the voltage across this resistor, we multiply the value of resistor R1 over the total circuit resistance and multiply it by Vs, and we get the 17.12 volts across resistor R1. Calculating the voltage across resistor R2, we put R2 over the total circuit resistance and multiply it by Vs, and we get that VR2 is 34.24 volts. Next, we're going to get the voltage across R3 and R4, which will be the same value as the two resistors are in parallel. So to do this, we put the resistance of this parallel section, which we again calculated earlier as RA, over the total circuit resistance and multiply it by Vs, and we get that VR3 equals VR4 equals 16.37 volts. Next, we get the voltage across R5. So to do this, we put R5 over the total circuit resistance and multiply it by Vs, and we get the VR5 equals 51.36 volts. Next, we'll get the voltage across the parallel section of which contains resistors R6, R7, R8 and R9. So you can see just three branches, and it's going to be the same voltage across each branch. And to calculate this voltage, we multiply the resistance of this parallel section over the total circuit resistance and multiply it by Vs, and we get 15.15 volts. So that's the voltage across R8, and it's also the voltage across R9. You can see this voltage across, which is also across R6 and R7, will need to be divided down further to get VR6 and VR7. So VR6 is calculated by putting R6 over the resistance of R6 plus R7, which we calculated earlier to be RB, and multiplying it by the 15.15 volts that we know are across these two resistors, and we get that VR6 is equal to 7.57 volts. The voltage across R7 is calculated the same way, so this time we put R7 over the resistance of resistors R6 plus R7 and multiply it by the voltage across these two resistors of 15.15 volts, and we get that VR7 is equal to 7.575 volts. So you can see that VR6 and VR7 are equal because it's the same value resistance, and when you add VR6 and VR7 together, you get the 15.15 volts that's across this parallel section. Next, we're going to get the voltage across the next parallel section, which will give us VR10. So you can see, to get VR10, we put the resistance of this entire parallel section, which we calculated earlier as RE, over the total resistance of the circuit and multiply it by Vs, and we get that VR10 is equal to 15.83 volts. So this is also going to be the voltage across the bottom section of this the bottom branch of this parallel section, and we're going to need to divide that down further to get the voltage across R14, R12 and R13 and R11. So to get the voltage across R11, we put R11 over the total resistance of this bottom branch of this parallel section, which we worked out earlier to be RC, and multiply it by the voltage across this bottom branch, and we get that VR11 equals 4 volts. Next, we're going to get the voltage across resistors R12 and R13. So to do that, we put the resistance of these two resistors in parallel, which we worked out earlier to be RF, over the resistance of this bottom branch and multiply by the voltage across this bottom branch, and we get that VR12 equals VR13 equals 3.83 volts. Finally, we calculate the voltage across R14, and this is calculated by putting R14 over the total resistance to this bottom branch and multiplying it by the voltage across this bottom branch, and we get that VR14 equals 8 volts. And that's the end of this tutorial.